Hello everyone, and thank you very much for coming out on a very cold day. So what we're going to be trying to do is understanding what are heat pumps, how do they work, the benefits over other forms of heating, how I would need to adapt my house. So we'll be doing a little bit on the thermal efficiency upgrades you might need to do to your house to get one of these machines. A little bit on the pitfalls of eco-retrofit, because there are things which go wrong when you do an energy efficiency upgrade, and it's good for you guys to be aware of some of those pitfalls, because what we don't want is a lot of people spending a lot of money and all of a sudden finally got like building defects or unhealthy internal environments. So just a little word on that. The cost and potential savings of working with a heat pump and running it. Grant funding, some of that landscape has changed very recently in a positive aspect. There's more money available for heat pumps. Do I need planning? So we'll cover that very quickly. And are heat pumps noisy? A question which lots of people sort of ask. So a little bit about me first. The company Deeper Green was something I started about 3 years ago after a long time of being a director of BBM Sustainable Design, which was a local practice of architects. I used to run a long time ago the office up in London, and then I moved down here with my partner Duncan Baker Brown, who some of you may know. But now I'm up and running on this. But these are some of the projects that I worked on over that 27-year time in that practice. This is the Romney Marsh Visitor Centre by Kent Wildlife Trust. It's I think it's the first public building made of straw bales in the country, and you can go and see that over at Romney Marsh. It's open to the public. Working on lovely private residential projects, some of the really early ones that we did in the early days of the South Downs National Park, trying to find the appropriate language to use. We did quite big scale work as well. This is down at Grand Parade, the University of Brighton, where we did a whole series of new interventions as well as refurbishments in the old building built in the 1960s. We turned what was a horrible microclimate where no one went out, they skulked in the corner and smoked cigarettes, into a place where we kept all those coastal winds out of there and the horrible eddying currents that there were. And it's a very successful project. And we also did, I think it was back in 2007, a long time ago now, a quite high-profile eco-retrofit. This was for the Two Piers Housing Co-op. It was part of a very large national study called the Retrofit for the Future program, working with the Carbon Trust and the Technology Strategy Board. There was funding, and we, out of about 70-odd buildings which went forward from the feasibility stage to build, this was the biggest one that was done. It's a conservation area. It's a villa, so in other words, 4 exposed external walls. And the target was to reduce the heating demand by 80%. That was for all the projects. And we achieved that. It was monitored for 2 years after it was finished. And so it was a massive success. But we managed to sort of keep the building looking exactly the same on the front. But just a very, very subtle thing here on the side elevations on the back, we added on this external wall insulation. So it's insulated on the inside on the front elevation. And we managed to get triple glazed windows in, which people said we wouldn't be able to do. But we managed to sort of finally, after about 2 months of negotiation with the conservation officer, finally managed to get in. And that is my own place, which is in Lewes. It's in the Baronsdown estate, built in the late 1960s. And they were built with a timber frame system build. We bought the place in 2011, and my wife and I, we sort of like worked out what we were going to do to make it nice and cozy. And we did this eco-retrofit in a 3-month hit of work before we moved in. And we then found out that after a year of living there that we were nearly carbon neutral in terms of our energy demands. It's very cheap to heat. We've only just put the heating on very recently, and we only need to put it on for about half an hour a day, and then we've got enough heat for the day. And what was remarkable about this one was we only spent about only about £50,000 on the actual energy efficiency work. But that also included a new bathroom, new kitchen, new floors. But yeah, so that was a really interesting, award-winning project. Let's move into our next topic, which is about what are heat pumps. When they originally built the Royal Festival Hall, you know this building in London, for the Festival of Britain, it was originally heated on heat pumps, and it used the River Thames as the medium out of which it was extracting some thermal energy from. And it actually used Rolls-Royce Merlin engines left over from the Second World War to power it. So not a lot of people know that, but that was an interesting fact which I learned when I was studying architecture. And this little slide shows the comparison of a heat pump, the external unit, which the thing which sits outside the building. This is an air source heat pump, and a fridge. So roughly, that's your size comparison of what these things are like. They're quite big, and they need to find a little place around the outside of a building somewhere. So it's not an insignificant consideration. But the fridge is also really important. Anyone know why a fridge is quite a useful comparison?
Because it's a heat pump.
Yeah, exactly. So heat pumps work on exactly the same technology as the fridge and freezers do. Basically, it has this ability to take an outside medium, and with this pump and special gases and condensing those gases and then expanding those gases, it's able to cool or heat if you run it in the other direction. And the magic thing really is, with a heat pump, it's working in the opposite direction to a fridge, of course, is that if you, say, put 1 unit of electrical energy into your heat pump, it takes an ambient medium, which is either air, ground, water. It combines that together to create a 3 times uplift in the amount of heat energy. So that's an amazing efficiency. And in the industry, we call that coefficient of performance. If you're comparing buying a heat pump, you want to look at the coefficient of performance to see how efficient it is. These are the 4 main types of heat pumps that you can get. The most common and the cheapest one is the air source heat pump with that external unit. Then you've got, probably the next most expensive is the one where we call these like slinkies, because they're basically big rolls of heat exchanger pipes which go out into the ground, and they're dug down a few meters but not very, very deep. And you basically have to have a lot of land area outside the building to do that, and it's just chaos when they're putting these in, huge amounts of excavation. And another one is the ground source heat pump, which is a borehole, and that's when they get drilling. With a rig has to come to your house, and you have to have a certain amount of area to do this, and they drill down incredible depths. And there's a little example here. 75 to 200 meters is typical in depth, and that's more height than the Brighton i360. So that's quite considerable. And they are very expensive for that reason. And as I mentioned with the Royal Festival Hall, some heat pumps do work. If you're right on a water body, you can exchange energy with that water. And this is a diagram sort of trying to show what actually happens. So there's normally a big propeller which is pushing the air across a heat exchanger here. And then you've got this special gas. And there's been a lot of development very recently in the types of gases that you can have in here. But you'll remember from when the ozone hole got discovered in 1987, I think it was, there's a lot of action that was made very, very quickly from the Montreal Protocol to get rid of all the CFC damaging gases in refrigerators. Do you remember that? So there's still some of those quite damaging gases used. Society has tolerated these ones, but they're still an issue. And we have to be very careful about how we decommission these to get rid of these gases. But some of the new gases that are starting to use are improving the efficiency of heat pumps. But it's this idea that the way the thermal dynamics works is that when it goes through here, this gas basically it expands, and then it's compressed with the pump action, and as it's compressed, it starts to raise the temperature further, and then it releases this energy as it comes into this expansion tank. And that's when it meets another loop which goes into your home and goes to a hot water tank. And then it comes back and the whole sort of system starts all over again. So that's kind of how the system works. That's what's going on in your fridge right now.
Can I ask a second question?
But in the other direction. So a hot water cylinder, well-insulated cylinder, usually gets, sort of put in. So that's the other thing. If you've already got a combi, many, many years ago in your house, you probably took out the old, gravity-fed system and got rid of the hot water tank, but now you've got to have it back. So that's another thing. So you need something outside and you need something inside. With a ground source heat pump, you don't need this, but you do need to have some equipment inside as well as that tank. But the main things that you need to remember about heat pumps is that they don't easily make very hot water. Now, as I mentioned just a moment ago, that the technology is getting better, and you do have what's called high temperature heat pumps coming out on the market now. But the higher they have to raise that water temperature, the less efficient they are, and then obviously the higher your electrical bills are going to be. But the thing is, if you've got a gas boiler or an oil-fired boiler, that's a really energy-dense fuel source, and they can easily make 70 degrees flow temperature in the water. And you can get away with having very, very small radiators or heat emitters in your home to compensate for the amount of heat loss that a home has. If you do this form of heating, there's two things really you have to remember. Is A, you have to sort of like try and reduce the amount of heat loss your home has got, and then we'll be talking about that in a moment, what sort of things they are. But also the heat emitters, the radiators, need to get bigger. You need to have more surface area so that you've got a lower surface temperature on those heat emitters, making enough heat for your home. Do you understand? So you have to make these bigger, but they're working at a lower temperature, and that makes habitable conditions. Okay? So it's the combination of slowing down that rate of heat loss and having a bigger heat emitter. So underfloor heating, for instance, works on even lower temperatures because it's a very, very large amount of area. And there's some issues as well about the siting of heat pumps. If you've got a badly sited external unit, say it's in a very dark, shady place, say it's in a light well where the air can't circulate around, what happens is you get a short circuit of air. It's not flushing away very well. And because you're taking heat energy out of that air, and if it's only allowed to just recirculate, you see what I mean? It's just going to get colder and colder and colder. Whereas if it's out in an area where if the sun is out and it's creating slightly warmer air conditions here anyway, and you've got good flushing of air coming through. So that can mean that your running costs are going to be lower than if it's badly sited. So these are just a few of the brands that are making them, more coming out all the time. So you get an idea about the fact that they can start from the really ugly and very industrial looking things, because they have literally just come out of air conditioning technology. And then this one's disguised with a bit of vinyl wrap around it with a photograph of plants. This one's completely black, and et cetera, et cetera. This one's known for being super quiet, whisper quiet. So the benefits over other forms of heating. There is a massive push within society to get us off burning fossil fuels. So we're running out of time to avoid catastrophic climate change. And of course, climate change is not the main problem. The main problem is the cause, which is us. So we're at the moment, creating the climate, humankind. So one of the big pushes we've been doing is we're trying to get more and more of our energy sources onto renewable energy. And wind energy, we're absolutely blessed in the United Kingdom. We have huge amounts of offshore wind energy. I remember some fact from when I was in my 20s that it was assessed that we had 2/3 the European Union's wind resource here in the UK. because of the offshore wind energy potential that we have. So that's one of the main reasons, and of course solar energy as well. And if we have a look at what's going on, this graphic is trying to show that we've got the years under here, 2019 to 2024. Beyond this point, it's purely speculative, but we all know that in 2022, with the invasion of Ukraine, that we had an energy price spike. This diagram is trying to show the price of energy in terms of gas and electricity. It's also trying to show the carbon intensity of those fuels. So the carbon intensity first. Electricity is slowly but surely coming down. And I've got a textbook back in the office from 2014 on eco-retrofit, and it says if you are on mains gas, it's not carbon beneficial to swap out your boiler, your gas boiler, for a heat pump. But that is no longer true because of what's happened. It is now more carbon beneficial to have a heat pump because of that amazing coefficient of performance it has. Gas's carbon intensity is not really going to change, right? But what will be changing, I think, is the relative cost between electricity and gas. I think gas eventually is going to be definitely way more expensive than electricity. And that's because we've got our own homegrown supply of renewable energy, and we're just grabbing all the gas that we can at the moment, aren't we? But it's going to run out, that's one thing, but also the poor old atmosphere can't absorb any more burnt stuff. So we're getting more and more global warming potential. So we're going to be pushed anyway. Society's going to have some push from government, hopefully, to come off the fossil fuel burning stuff. And heat pumps are really the only solution that we've got which makes sense in this new paradigm. Biomass has often been talked about, and about 10 years ago, everyone was going, oh, biomass, let's have biomass. But the issue is it's not carbon neutral, in my opinion. It was touted as being carbon neutral. But the thing is, it takes about 30 to 60 years to make a decent harvest of wood, but it can take in a big biomass burning power station, 60 minutes to burn that wood. So it's 500,000 times longer to grow it than it does take to burn it. That is, for me, not carbon neutral at all. Other forms of heating, so if you've got one of these kicking around, we have one of these in our office. It's so cold. This is an oil-filled radiator that holds onto its heat even after it's gone off. 1-to-1 efficiency, not 1-to-3 efficiency. Another form of electric heating, you probably all know and have lived with, electric storage heaters. So these work on Economy 7 tariff. An Economy 7 tariff was sort of invented so that it would promote using electricity at night because of the big steam-driven turbines of power stations. They have to keep these enormous turbines going. They can't spool them down and spool them up again the next day. So to make that electricity sort of like attractive to us to buy, Economy 7 was introduced. So it is still marginally cheaper. It's not as cheap as it used to be relative to normal daytime tariffs. And that's probably because we're using power stations less and less. But these are clunky. We all know that they can't really sort of like react to changes in temperature outside. My storage heater, we also have a storage heater in our office, and that's on right now, and we're not working there over the weekend. So it's a really blunt instrument for heating, but it is what it is. It's quite clever that it can take energy from night and then you release it during the day. Oil, or LPG, liquid propane gas. Propane gas is marginally worse than gas in terms of global warming potential, but oil is much worse. If you have a rural location, if you're out in the sticks, I think it makes a huge amount of sense to swap out right now to heat pumps and get rid of that horrible, ugly green tank. And you can be, on the basis of you're doing something really good for the environment. So I am seeing more people out as I travel around on my bike. I see out in the rural areas more and more heat pumps going in. You can see them. What about hydrogen, green hydrogen? But you make hydrogen basically for a fuel. This is all something we're talking about as one of the new technologies that's going to come along. But the issue is we have to use energy to make hydrogen fuel. And it's very, very likely, the experts say, that the aviation industry, for instance, is going to be first in line to have this so-called green fuel. So if we can make enough renewable energy, electricity, during the good times during the summer, we might be able to make enough hydrogen to have something of an aviation industry. But we're certainly not going to be sort of like swapping out, in my opinion, from gas in our pipe work to hydrogen. I don't think that's going to happen. So the issue we have really is that, just to remind you of our existential predicament, is we've been burning stuff so long now. Since the Second World War, we have vastly accelerated our reduction of the ecological capacity of the Earth to sustain life, and we've got rid of so many of these non-renewable energy sources now. Everything's connected. We now have 8 billion people on the planet, and they all want some of the resources. They all want some of the remaining arable land. And climate change is reducing the amount of arable land that we have. So we have so many issues going on at the moment. There's chaos going on because of exponential growth, because of exponential unchecked population growth. We have got a very, very difficult situation coming up. But heat pumps, I think, are one of the solutions, one of the technologies which is a positive way forward. I've made the commentary that human beings are not very good at seeing slow-moving existential threats. We did an amazing job during COVID because that was very immediate and we responded. But evolution has made us, that's coming down the line. That's for another time. But actually, this is a really, really big issue. It's just continuing to gain and gain and gain momentum, and we're not really doing enough about it. We still have, all of us, including myself, our heads in the sand about it. Okay, how much do we need to do to our house to make it energy efficient so that we can put a heat pump on? So this is like a basic sort of principle diagram about a conventional house with not much insulation or no insulation, and you've got your boiler, and that kind of keeps up with the amount of heat loss that you need during the winter months. But if we can get a super insulated house, perhaps with some intelligent bit of a passive solar gain, you've heard of passive house technology, you can even get rid of your boiler. You can just heat your house with your body temperature, you about 120 watts of heat energy off your average adult, with cooking, etc. So yeah, it is possible, and we do have a lot of examples of we've made net zero houses and so forth. But it's very difficult to do with eco retrofit. Just to remind you that one of the things we need to do is slow down that heat loss because of this issue of the heat emitters not keeping up. So you can insulate a building from the inside, and on this beautiful building, if we would insulate here, we would probably go, right, on the street, we're definitely going to have to look at insulating on the inside of that wall. But the thing is, if you do that, there's a really strange, horrible situation that arises between the transition between the old fabric and the new insulation. You can get this thing whereby warm, moist air condenses on the face of that cold, original, uninsulated building fabric. And that interstitial condensation, if it hits the dew point, it becomes water which doesn't really escape very well. It's gone out of its gaseous state. It's in there. And that can cause all sorts of problems. It can cause building defects. It can cause unhealthy internal conditions because you can get mold growth, the spores of which can get through the cracks and come out. So we don't like doing this too much, and if we do, we work with very porous, vapor permeable insulation which can dissipate that moisture back in. But the U values, the thermal performance, we can't achieve very high performance like we can if we insulate on the outside. You can insulate a lot more on the outside of a building. It's like a big sort of puffer jacket on the outside of Lewis House. And it's safer for the building, it's safer for you. But what we end up doing is probably a mix of all these things. So the front elevation, we have to do usually the inside, if it's reasonably historically important, heritage value. But on the rear, we can probably sort of safely say we can do external insulation. There's stuff for lofts, there's stuff for inhabited roofs, suspended floors, and also for ground-bearing slabs. Some of these are on the panel over there. And then the insulation materials that you might need, these are all man-made materials, usually from petrochemicals. This type of insulation here, we call this PIR insulation. It's very high performing. It's made from derivatives of oil. You can use this for external insulation. You can also use this. This is basically rock. And one of the brand names is Rock Wool, but there are other brands, of course. And but that is made of melted rock, basically, and spun into a fibre. And this is what we have to use on tall buildings because it's completely inert to fire. It doesn't burn at all. This is the stuff that you might have seen in your roof, your loft. So this is the same stuff as that, more or less, but it's spun into a quilt. So a spongy quilt with that. That's quite resistant. But yeah, all these use a heck of a lot of energy to make them. But for instance, that is amazingly well performing, better performing from a thermal efficiency point of view than the mineral felts or the glass quilt. But there are a whole series of other more environmentally benign materials, and these are the ones we would anyway advise using if you're going to insulate on the inside because they're vapor permeable. So for instance, here is a timber fibre bat, and you put lime plaster on also, which breathes, and that can get rid of any interstitial condensation in there, in that wall thickness. There's flax, there's hemp, there's even recycled jeans being made into insulation. The problem with this is that it seems to be always more expensive than the man-made stuff. And that's a problem for the industry, but the gap has been coming down. I've known the industry long enough to know that most people don't really get into eco-retrofit. They usually fall at the hurdle of it just costs a lot of money. And I often say to people, a good eco-retrofit costs as much as a decent extension. And some people go, I want the extension more, or I want to convert my loft more than I want that eco-retrofit. And that's a problem. I think that needs to change. I think, people do a really bad conversion of their loft, they all of a sudden have an overheating issue because they've done it poorly, and they can't be up there during the summer months. What they ought to be doing is maybe spending that kind of money, I think, on making their buildings energy efficient. But there are some projects where you can spend loads of money, like hundreds of thousands on your eco-retrofit, and then there's everything in between. I sort of realized that there was a bit of a mismatch in terms of what people know about it, how much it costs to do it, and that some of the methodologies just weren't there to help people. So I thought if I made a sort of a heat loss calculator, which is really quick to sort of like do an appraisal, and one which is a little bit more meaningful than an EPC calculation, then we can work out specifically what elements of the building are the best things to tackle. What we do is we do a measured survey of the house. We have our ground floor, our roof spaces, windows, doors, external walls, and a bit of mansard roof on this particular. And every one of these has got a different thermal efficiency. A U value is attached to that. I don't know if you heard what a U value is. But anyway, that's our thermal envelope. That's where we are losing heat energy out of the building. And then we punch all these into the calculator. So ground floor, walls, street, rear, loft boarded, and so forth. These are the U values. So that's the thermal efficiency coefficient that we use to sort of work out how efficient it is. And that gives us a proportion of the whole kilowatt hours per annum. And it's not just about the thermal heat losses, it's also about ventilation heat losses. So we have to do a calculation here as well, talking about the number of air changes per the volume of the internal spaces. So this is a bit of a wet finger in the wind calculation to work out how much heat energy is just being lost through the fabric of the building, and then we come up with a total figure. In this case, it was about 10,000 kilowatt hours per annum, or a peak demand of about 6.2 kilowatts. The calculator then sort of partially fills out the propositional ones, and we start to play around with the U values of these elements. And we also then have extra columns where we put a guesstimate of the cost, and that then on the end gives us a carbon versus cost benefit ratio. And the deeper the green, the better the result. So yeah, it's quite a lot of money, but this is a deep eco retrofit at about £55,000 just for thermal efficiencies. But we've got quite a good sort of reduction. We've made some improvements, some guesstimated improvements on the ventilation heat losses. That's come down from about 9, I think it was on the previous one, to 4. And we're getting a really good reduction, 60% reduction, more or less, in the heating demand. And then we'll look at specifically what are the technical retrofit measures we're going to try and achieve. And then this is where we might end up with. So we have a comparison at the end of the study. This was a very big house, a lot of surface area, and it was just so much money to treat the whole house, a ridiculous amount of money. So we started to look at, okay, well maybe we'll make a heat bunker down the lower ground floor where they spend most of the day. And if they're just working from home, that's actually quite a good thing to do. So you can get through without heating the whole house to 20 odd degrees Celsius. So we're starting to get clever with the spend. And then we can also help, I mean, if we just leave it there with the client and they can then go off and do their own thing, and we've done a lot of that over the last year. Or we can get all the permissions that may be required. So there's planning permission might be required, listed building consent if you're in a listed building, conservation area for a lot of Lewis, for instance, you're in a conservation area and you might need to get that level of approval. And there's building regulations approval as well. And then if it's a very big project, it might be sensible to keep the architect on if you're doing an extension as well. But typically you wouldn't expect an architect to be involved during the build phase. Just a quick word on pitfalls of eco retrofit. Does need a dedicated talk, I have to say. But every single one of these bullet points could be a dedicated talk. And when I do my own continuing professional development, I have to sort of see the latest technology that's coming up. I will do something, for instance, on thermal bridging. I will go and go to a talk on thermal bridging, find out all about that. Unhealthy indoor environments and so on and so forth. But it's really important to think about. So lack of adequate ventilation, that's something which comes up time and time again. Cavity wall insulation failures. So not all types of cavity wall insulation are right for the job. And indeed, if you're in a very exposed location, maybe you shouldn't have it at all. Thermal bridging is where you've got no insulation for a short length. Usually we get it at junctions around windows, for instance, or where you've got timber structure from the roof coming down. The wood doesn't perform as well as the insulation. So you can actually see literally condensation on where the rafters, for instance, are exposed below the plasterboard. That's what thermal bridging is about. Interstitial condensation is the stuff which happens inside the thickness, as I mentioned earlier, inside the roof, inside the walls, and it's a problem. And that's where we all have to become little building physicists to understand what's going on. It does get complicated, as I mentioned earlier. And we have these spin-off issues about, you could be accelerating building defects. And a classic one is, if we did insulate this wall, and we've got roof joists which go into the brickwork, that timber joist is going to be in very, very cold, possibly wet if it's a solid wall, possibly wet brickwork, and then it goes through insulation and into a warm environment. And that's an absolute recipe for disaster. And what we don't want is the end of that timber rotting and then falling out all of a sudden. So there's all sorts of issues that we need to look at very carefully. And we've got solutions for, but they unfortunately cost money. Unhealthy indoor environments, I've mentioned already that you can, if you've sealed up everything and you're not really changing the air properly, or you've got mold growth happening, you can get very, very unhealthy indoor conditions. But a lot of people aren't really kind of switched on to that, it's particularly when they're struggling to heat their homes. There's also poor levels of understanding generally in the building trades about eco-retrofit, and they're not necessarily doing the right thing. And I've been speaking to some people who've done eco-retrofit locally, and they've known more about these issues than their builder has. So they've been teaching their builder how to do it. And it occurred to me that part of the The reason that we have something like the Climate Hub is that we can do signposting so that you guys are more informed. You can basically police your eco-retrofit work a bit better, but also the building trades, they need to be signposted to where they can get accreditation, to where they can get better understanding of what goes on. So yeah, the Climate Hubs I think are fantastic in terms of disseminating information. But there's also these organisations. Green Register, they do charge for their seminars, but they're very, very good. Very, very high level information that gets put out on the Green Register talks. AECB, that's the Association of Environment Conscious Builders, for those who do care in the building industry. And there's the Architects Climate Action Network. They also have every now and then really good free talks on eco-retrofit. And you can join ACAN. And then there's the Retrofit Academy. So that's been set up since the 2008 closure of the Green Deal. You may have remembered the Green Deal. But some of the people behind that sort of said, okay, we need another way of doing this. So they set up an academy for training people to assess eco-retrofit, to plan it, and then also to carry it out. So they do the training for builders as well as consultants. Costs and potential savings. This is a great quote from the Low Energy Transition Initiative, or London Energy Transition Initiative, I think it's called, LETI. They do some great free downloads, by the way. So the key message is, if you do nothing else, make enough fabric improvements to switch to a heat pump and avoid putting in fossil fuel systems at all costs. So that's what people, really, really expert people in the know are saying. We were talking about what sort of, what do I need to do to my house to put a heat pump in? Well, there was actually a recent study which took about 750 homes across Great Britain who put a heat pump in, and some of the big sort of things which came out of it was that pretty much 15% of the buildings needed an upgrade. But it has shown that with the latest heat pumps, you don't necessarily have to do that much to be able to heat your home. Found this on a local business based up in Hartfield called Biosun Energy, and this is what they're saying: with a 200 square metre home, well insulated, that you could actually be spending 70% less with electric heating over oil boiler, 70% less than the normal direct electric heating, 54% less on an oil boiler, and 29% less with a gas boiler. But I think that, again, just to stress, that's with a well-insulated home, probably a new build. But it does give you an indication that things are going in the right direction. A few more points on the installers. Make sure that your installer is MCS accredited. That's super important, otherwise you won't get the grant. Make sure the heating engineer does a thorough and accurate heat loss calculation. We've all been used to having our boilers put in. They don't really do much of a calculation to do that, because you've got such a big margin of error with a gas boiler. That density of fuel is just so good. But with heat pumps, you've got to be a lot more accurate in sizing the heat pump and the size of all those radiators and heat emitters. And at the moment, there's probably only about 3,000 accredited heat pump installers, whereas in contrast, there's about 130,000 gas-registered heating engineers. So there's a little bit of lag there. We haven't got really that many people who can do this stuff at the moment. So it is difficult finding a good installer. Training for heat pump installers is also being subsidised, but at the moment there's no single clear route to qualify as an installer. But this is an example of a worksheet from the CIBSE. CIBSE is basically the Building Services Engineers Institute, basically. And this is their methodology for doing a heat loss calculation. This is just for one room. So all the data you've got to sort of fill out in their methodology. It's a lot of work. But that basically sizes all your radiators and so forth. But you've got to put the U values in, and for that wall, that roof, and it's a lot of work. But another thing to sort of point out is what can happen to your projection of running costs over time relative to the amount that you invest. So on the left, we've got these yellow columns going up. That's kind of like a measure of how much you're spending in investment terms. Here's the money column going up to 100,000 there. These are the years of running along the bottom on the x-axis. And if we are retaining our gas boiler, this is probably what's going to happen to your running costs over time as we go into the years into the future. But if we spend, say, £10,000 on putting a heat pump in and changing radiators and so forth, we might start to get running costs like this, which then become cheaper at this point after, say, 6 or 7 years than what's happening with our gas prices. We might get a return on our investment after about 10 years or so. This is all speculative, but it gives you the idea about what's going on. And then, light or a deep eco retrofit, perhaps with a really, really good ventilation system, you're going to get these sort of almost flattening of, almost cost neutral. And until we get to things like adding solar panels, on-site energy generation, where you're actually making your own energy, and then if you do all of that, £100,000 of investment, maybe you're going to have money coming back towards you. Part of the study that we do, we will do a comparison, working with the kilowatt hours per annum that we've managed to get it down to. We then compare the carbon intensity of what you'll save by swapping to a heat pump. So if you stick with gas, 1.3 tonnes per year, or you go down to 0.262 with a heat pump. And then the actual gas and electricity is compared in terms of running costs. So gas in this case is still a little bit cheaper, but not by much, than the air source heat pump. And the interesting thing is that these coefficients are changing. So the carbon intensity actually changes every day, depending on how much wind and how much sun is going. But you can generalize, and this figure overall is going down. These figures, these are the capped gas and electricity prices, they're also fluctuating. So every time we do this, we have to change these coefficients. So this is the grant funding. At the moment, private residential project for an air source heat pump. This bit here I hadn't changed since I did it in February, but I think this is now changed. It's still a lot of money to make that conversion. But we have recently heard of someone in Shoreham that put an air source heat pump in a 3-bed terrace house, and the grant was such that including 6 radiators, it was just £700 out of their pocket to put it in. So things have changed. Octopus Energy now, I think they've actually bought a manufacturer in Ireland of heat pumps, so they're going to really start rolling it out. They want to, in effect, make it at the same price, if not cheaper than putting another gas boiler in. British Gas and the new entrant in the industry is called Aria. They've also been driving down costs. I mentioned earlier that the different forms of heat pump, like ground source heat pump, they're very expensive. So very few people can afford £25,000 to £40,000, but that's typical for an off-grid rural location. But this is a big one. If you're getting close to replacing your boiler anyway, then you're going to have to spend quite a large sum of money anyway to get something new in. So you might as well make the jump at that point. And this is straight off the government's website. This is the boiler upgrade scheme, and it does change very rapidly. So we can't constantly having to go back to look and see what the current situation is. But the grant for an air source heat pump at the moment is £7,500. But before October, it was just £5,000. So that was one of the good news stories for the environment from Rishi Sunak's announcements back in October.